All right, good morning. Good evening. Yeah, let's get started. At the end of the previous lecture, we touched upon a special kind of field, vector field, called conservative field. Okay, so let's continue, and so let's look at conservative field and what are some of the properties associated with the conservative field. So first of all, you need to understand that conservative field, it's a special kind of a vector field. Okay. Why is it a special kind of vector field? Is because this type of field is a gradient vector field, technically. So it's a gradient vector field. By saying that, it basically means this vector field is a result of calculation of the gradient vector based on a scalar function f. So you obtain a scalar function, you calculate its gradient vector, you produce a vector field or vector function, and that is a very special kind of vector field, which we call a gradient vector field. And this is also called, I'll see this F is also called conservative field. So in the previous lecture, we demonstrated there are two special conservative fields. One is the gravitational field, and the other one is the electrical field, right? Electric field of a point charge. So the next question we're going to look at is a couple things is, okay, just bear this in mind here. Essentially, what is so special? About this conservative field? Okay. So first specialty, we're going to cover a theorem. It's called fundamental theorem of calculus. Okay. So if I stop here, I think it should actually remind you, oh, that's the 172 fundamental theorem of calculus, right? But this is the fundamental theorem for line integral, so more specifically for vector line integral. So what is this fundamental theorem of calculus? Let's write down this description of this theorem here. So given a curve C, so let's say the curve C running from initial point P0 to P1. So let me illustrate this curve C at here. Okay, let's say this is curve C in 3D space. Start from the point P0 and end at a point P1. Or in terms of parametric equation, R of t. So let's say the C at here is described by a parametric equation R of t. Okay. Then we could see that the t, let's say this is when t equal to A, this is when t equal to B for the location P0 and P1. So that means we have a parametric equation. The range of the t goes from A to B. Okay, so this is a curve C, description of curve C. And the curve C is currently immersed in the vector field, okay, and a vector field F. Okay. And the F, okay, let's assume F is a result of this gradient of the scalar function. So F is a grading vector field. Then we know the F is also conservative field, right? Yeah. So that's the nature of this vector field. And we're going to later to look at it. How do I know it's a conservative field? If it is conservative, then how could we find a certain scalar function F, okay, so that we can get this vector field F? Okay. All right, so then now you've got everything. You have the vector field, you have the curve C. Then, okay, if we're going to integrate, okay, we're going to integrate this vector line integral this over the curve C. So integrate this vector field of vector function F over curve C. And that's what basically it's vector line integral that we learned, right? It's equivalent to write it as a C F dot dr. If you recall that formula from the previous lecture, it's equivalent to write it as dr over dt and then dt. Right? So all of these writings, it's all the description of vector line integral. It's all the same thing. And then this vector line integral, okay, the key here is this. So you can technically you can calculate this vector line integral as the approach that we have done. So if you've got a parametric equation for R of t, then you can certainly calculate the derivative, substitute the parametric equation into the vector field F or vector function F, do the dot product, and then right you get the results of the vector line integral. But according to the fundamental theorem of calculus for line integral, and because the vector field F is a conservative field, now this vector line integral actually now can be just simplified into equal to fp1 minus f of p0. Okay. So this is the idea of the fundamental theorem of calculus. So this equal sign follows all the equal signs from the top. Okay. So what does that mean? Basically, you don't need to calculate this vector line integral. All you need to calculate is calculate the value of the scalar function f at the endpoint t1 minus the value of the function scalar function small f at the initial point p naught. You subtract each other, and you get the result of this scalar line of this vector line integral. So that's what this fundamental theorem of calculus for line integral. So if I recall to jog your mind here, when you calculate the integral of a function, and if you know its antiderivative is capital F of x, then sorry. If you know the antiderivative is capital F of x, then the result is f of b minus f of a, right? And that's this is a fundamental theorem for calculus in 173. Okay. And this is the fundamental theorem of calculus for line integral, right, in this course. See the difference, okay? Yeah. Now this property out here, or this theorem in here, and as I'm gonna put a comment here, it's also basically equivalent to saying path independence. Path independence, okay? Basically, if you want to calculate vector line integral, it really doesn't depend on the path from P0 to P1. As long as the vector field you know is a conservative field, if there's any curve connecting P0, P1, the end results of the vector line integral is the same. That's called path independence. So I'm going to talk about this next, okay? So in terms of proof, I think I'm going to skip the proof right here. Nobody likes the proof, but take a look at the lecture notes, okay? It's not a very long proof. Excuse me. Okay. So take a look at the lecture notes in terms of proof. And the idea is basically, right, I want you to firmly imprint your mind. Number one, are you dealing with a conservative field? So this is number one key points. It has to be conservative field. Otherwise, this won't work. Number two, if it's conservative field, then the vector line integral right here, okay, over a certain curve C within this vector field only depends on the value of the scalar function f minus at the endpoint minus the value of it at the initial point. All right, yeah. So for this relationship, right, the f equal to del f, small f right here, okay, we call it a potential function. And so we got a name for it. It's called a potential function. I mean, it's a scalar function in general, but in this case, we call it a potential function because the vector field f is a direct result of the gradient operation on this scalar function f. It's a potential function. So del potential function give you a conservative field. All right. So let's take a look at example first of how this theorem, okay, and here can actually help us to calculate some of the vector line integrals. Okay. Example number one, and it's just one example should be enough. Okay, I'm gonna bring one of my pictures into OneNote. So this is the question that we're going to work on here. All right. Okay. So currently, you can clearly see there is a vector field, okay, within the 2D space. It's a reduced level of. So here is vector field. It's described as y I hat plus x j hat. And if you plot this 2D field, and you can get all the arrows, right, as described over here. And within this vector field, you have a closed loop. Okay? You have a closed loop curve. Consists of 3 segments, C1, C2, C3. So the C here equal to C1 plus C2 plus C3. And you can obtain the parametric equation next. So the general question here asked is, so then what is the vector line integral over this closed loop curve C? Okay. Because there's 3 curves, so you can calculate the vector line integral like a piecewise integrals. So basically you calculate 3 different curves, which is okay, right? Yeah, just piecewise integration. Okay. Now, doesn't matter what choice you're going to choose, right? Whenever you see a vector line integral integrating certain vector field over a curve C, the first step is always you look at it. Did the question give me the parametric equation for each segment of the curve, or maybe just one segment? Who knows, right? So if it doesn't quite give it to you, then you have to write down the parametric equation for the curves. So let's write down that first, and then we'll look at basically what can we do with this vector line integral. Okay. So first thing, C1. Okay, what is the parametric equation for C1? Okay. So let's call this R1 here. C1 is a straight line going from A to B, and the coordinates of the B here is at x equal to 1, y equal to 0. So that's the coordinates of B. Right? So 8 is a straight line, so it's going horizontally, meaning the y is actually not changing, right? So y should be always 0. And x changes from 0 to 1, so you could just let x equal to t. and t, right, go from 0 to 1. So that describes the segment, straight line segment A to B. Okay. C2, let's call this R2. Okay. And that's the part of the BD curve. This curve, the question should tell you this. This curve is a part of the circle. Okay, so part of a unit circle. So if you finish this, it's part of a unit circle here. Right? So if it's a unit circle, so this circle is x squared plus y squared equal to 1. Okay. So we have done parametric equation for circles before. If it's unit circle, meaning radius is 1, so you can use cosine t and sine t to represent this circle. But of course, you have to choose the t's range. So basically go from here to here, B to D. Right? We call this, is the question should tell you it's a 45 degree, right? A piece of a pizza over there. Okay? So then t go from 0 to pi over 4. Okay? So the question will label that for you. Okay, so now you can label this t as 0 to pi over 4. So that's representation of the C2. And the last piece, okay, is a parametric equation for the DA, right? So this part of the segment, it's again a straight line. Okay, the line goes from D to A, right? So technically, first step, you have to find what is the coordinates of the point D, right? And then you can construct the line properly. But you know this is a pi over 4, 45 degree. So whenever you have a line 45 degree, I mean, this line is what? Y equal to x, right? Yeah. So the line will be 40 because this is your slope, 45 degree. Okay. So technically, I know this is 45 degree. This is y equal to x. So the line could be, if you let the x equal to t, okay? So that's your line here. But currently, you can see the t, right? It's go from somewhere from D back to 0, okay? So what is the coordinates of the point D then, right? So maybe we should get the coordinates of point D before we can write down the parametric equation for the range for the t, right? Yeah. So for the d at here, I mean, this is 45 degree. This d is on the unit circle. So then what's the d's coordinate? D's coordinate must be cosine pi over 4 and then sine pi over 4, right? Yeah. And that gives you root 2 over 2 and then root 2 over 2. Okay. Yeah. So then the curve DA or C3, basically, so C3 is a part of the curve goes from 2, 2 back to 0, 0. Okay. Yeah. Then for the range of the t here, right? Because I said TT, the range of the t. So you could use a little bit unconventional. You can see, okay, t go from root 2 to 0. Okay, so often in time we said t go from 0 to 1, right? A positive change, right? But it's okay. So t go from root 2 over 2 to 0. So basically, when the next step we integrate, then you can integrate as root 2 over 2 to 0, right? Okay, and that is equivalent to negative 0 to root 2 over 2. Does that make sense? Yeah. So that's how you can construct this parametric equation for C3. Of course, if you're not very comfortable to let t go from a root 2 to over 2 to 0, if you prefer that t has to start from 0 and end up at something, a positive number, then you have to change the parametric equation, right? Instead of a TT. So you're gonna have to, how do you change that? You know, I'll let you to work it out. Okay? Actually, part of the tutorial for either this week or next week has a demonstration of doing that. Okay. So now once you get the parametric equation, the next step, traditionally, what you need to do is, right, according to the formula of the vector line integral, you need to calculate derivative. You need to substitute the parametric equation x of t, y of t into the vector function f. Okay. Of course, you have to do this for each one of the line segments. Okay, and then you add them up, you get the total line integral. Okay. However, okay, I'm not going to do this in this way because fortunately, the vector field, okay, we have over here. Okay, so f, okay, we can find. Right now, I just write it down here. We can find that this vector field f, okay, which is y, x, okay, equal to del f, where f equal to xy. Okay. So if you don't believe me, you can plug it into xy into this gradient. All right, this is your f. So first, this is partial f partial x. This is partial f partial y. If you calculate partial f partial x, what do you get? You get y, right? You get partial f partial y, you get x. So this vector field is a result of the gradient operation of scalar function or potential function xy. Okay. Now you might wonder, how did you find this at y equal to xy? So that's the second part of the question we're going to deal with next. Okay. Yeah, how we can find this one here. But for now, just trust me that you can find this scalar function f somehow that give you this vector field. Now, this finding is very major because that means, right, this one is conservative field. If it is conservative field, then I have a powerful tool right here. That's the fundamental theorem of calculus. I don't need to calculate this vector line integral. I just have to use this formula to get the value of this vector line integral, right? So that's what I'm going to do. I'm going to apply this formula to each one of the curve segments, right? So for C1, right? So we're talking about the integration over C1 f dr. Okay, this is a vector line integral. Now, I'm not calculating it. I'm calculating the value of this scalar function f. C1 go from A to B. Okay, so you're talking about the end point is B and the starting point is A. So you try to subtract these two to get the value. Okay, so then what is the value of a function f at location B? Right, so location B, so let's write down a few coordinates here. Okay? I already write down the coordinates D, so I think I can write down a few other coordinates. So B has a coordinate of 1, 0, right? X equal to 1, Y equal to 0. A has a 0, 0. And then D, I have already have it, so √2 over 2. So those are important, A, B, D, right? 3 different locations. So now, let's see. What's the value of a function f at the B? B is 1, 0. X is 1, Y is 0. So meaning you get a 0 for this one here. F of A is 0, 0. So you got another 0. So the overall line integral from A to B should be a 0. Right? According to the fundamental theorem of calculus. And then for C2, okay, we can do exactly the same thing. We integrate over C2 and we calculate the value of the function, small f, from the B to D. So you use the value of the value of f at the D minus the value of f at the B. Okay. At the D, your coordinates is √2 over 2, √2 over 2. Here's your function f. So x equal to √2 over 2, y equal to this, right? So multiply together. Minus f of b, we already got it, 0. So altogether, that results give you 1/2. Okay. Last step for C3. And this goes back from A, so f of A minus f of D. And each one of the value, we already got it, so 0 minus 1/2, so negative 1/2. You got 3 values, and you add them up. So the total integral, vector line integral equal to the addition of all of 3. So 0 plus 1/2 minus 1/2 equal to 0. Right? As a matter of fact, for this question, I don't even need to do these 3 steps here at all, because this is a conservative field. If it's conservative field, as you integrate over a closed loop, you will end up with a 0, right? Remember the fundamental principle in dynamics. If you do work in a conservative field, as you do the work in a closed loop, the end up the work, total work is what? 0, right? So that's the idea. But this is just demonstration, basically. Within a conservative field, so within a conservative field, if you integrate over a closed loop, it will be 0, right? So C here is a closed curve or loop. That good? Yeah. So this is one of the very important observations. Again, it's an extension of this fundamental theorem of calculus, right? So I need to summarize a few properties, okay, or make comments here. So there are 4 different equivalent properties. Okay, so there are 4 equivalent let's call it properties. Okay. Number 1 property. Okay. You can claim that F is conservative. Okay. If you claim F is conservative, okay, then it's the writing we just wrote it down. Then if you integrate vector line integral over closed curve C, you will have a result of 0. Okay, so that's number 1, right? And number 2, now if the C is not a closed curve, okay, so look at the integral here, there's no circle indicating a closed curve C, then you have this so-called path independent. Okay, so path independent. So this is also very easy to understand, because given 2 points, P0, P1, technically you can create infinite number of curves, right, from P0 to P1. Okay. So C1, C2, C3, you can create an infinite number of a path. However, because if the F here is conservative field, then according to the fundamental theorem of calculus for line integral, the end results only depends on, right, F of P1 minus F of P0. It doesn't depend on which path it goes from P0 to P1. So that's what we call path independent. Okay. Path independent is a very common concept. I think if you look at your thermodynamics, which is your current learning, there's also a path independent internal energy, right? The change of internal energy is path independent. Okay, so that's number 2 property. Number 3, so if you see F is a conservative, it's equivalent to see that F is a gradient field, or F equal to del F. So this is also equivalent. So basically, where does F come from, right? F has to be from the gradient operation of a scalar function F or potential function F. Okay, that's the connection, right? If F is a conservative, it has to be like that. Okay. Number 4 is a little bit less common saying here. Basically, if you recall, for F vector field, it always has, if it's a 3D field, it always has 3 components, M and P, right? Then we also know this F, okay, is a result of del F. So basically means the 3 components of the vector field F has to be related with this scalar function F, which is Fx, Fy, Fz, right? So del F is partial F, partial X, partial F, partial Y, and partial F, partial Z. So they has to be related through this relationship right here. So that means the M is a result of partial F, partial X. The N is a result of partial F, partial Y. And P is a result of partial F, partial Z. Okay. So these 4 properties, so we call them equivalent. So whichever that you can demonstrate is true, then the other 3 will naturally be validated. So that's what we call they are equivalent, right? And it's all based on a common knowledge that F is actually conservative. Right? So the next time, if you happen to have a conservative field, and we'll show you how you can prove that the F is conservative, then the vector line integral can be calculated much simpler, okay, than the traditional approach. Okay. So now it begs a question here. Okay, so it begs 2 questions actually. Number 1 question is, how do we know a certain vector field F is conservative? Okay. So if you're given a vector field by a certain question, then how do I know it's a conservative field, right? So that's something that we need to be able to figure out. And next thing is, suppose that, okay, you actually find it out, is okay, so F is conservative, okay? Suppose that you somehow figured it out. Then the next question is, right, so what is its potential function? Small f. And what is the potential function F? Because if F is a conservative, and we know that F, right, if you take gradient operation of the scalar function or potential function F, then you should get back to this vector, the conservative field F, right? So the question basically is, then how do I find out the potential function, right? Just like this, in this example here, you know, you have a vector field Yx, and I'm telling you, right, I said, okay, I find it out. The potential function is xy. But how did I find out, right? That's what we want to demonstrate at here, okay? So these 2 questions are what we need to answer at here. I'm not sure we can answer all the 2 questions, but let's tackle the first one. Basically, how do we know that F is actually a conservative field? All right. Okay, so And then I'm going to present you with another theorem to obtain this answer for the first question. Okay. So let's look at another theorem in here. So let's write down a field F is conservative if and only if and only if del cross F equal to 0. So del cross F equal to 0. So this sign here is a cross product. And this one is that del operator, the greeting operator. Okay, so we'll see what this means at here, right? All right, so first of all, the del operator is an operator. So you have 3 partial derivative actions, right? So without inserting any functions. So this isn't a vector, basically it's a vector operator in theory, right? So you have a 3 component, each component is the first order partial derivative. And F is the vector field, okay, given by the question. So there are 3 components, M and P. Each component is a scalar function of X, Y, Z. So the theorem basically says, you want to know if this is a vector field F is a conservative or not, calculate this cross product. See if it's a 0 or not. If it is 0, then this vector field is a conservative field. All right, so now I can show you how to calculate this cross product. A cross product formula is your first row is ijk, and second row is the first vector, but it's not a real vector. It's not a real numbered vector, right? So the vector here is partial, okay, partial x, partial y, partial z. The last row is the function, is a vector function f, m, and p. Okay, so this is the cross product formula. You calculate the determinant of the 3 by 3 matrix, and you get the cross product formula. Right, so we used to do, we replace numbers for each row for the second row and the third row, but now we replace the second row with a del operator, and the third row with the vector field F. Okay. So if you calculate this cross product, okay, just treat each one of the element as if it's some sort of a number. But for example, if you multiply this element with this element, okay, that means you're calculating partial derivative n with respect to x. If you calculate the multiplication of these 2 elements, then you calculate partial m with respect to y. So that's how they operate, right? So the end results of this product, okay, the cross product is partial p partial y minus partial n partial z I hat plus partial m partial z minus partial p partial x g hat, and then plus partial n partial x minus partial m partial y, okay, k hat. This is the results of this 3 by 3 matrix determinant, and that's the result of the del cross F. As we're going to learn, okay, this one also has a name. This is called the curl F. So we're starting to see, okay, for the last couple of weeks, we're starting to see all of the operators showing up here. Remember, we have a del applied to F. This is called a del operator. So now we got the curl operator. So del cross, it's a curl operator. And the next, in probably the last week, we're going to learn a del dot. It's called divergence operator. Okay, yeah. And this curl has quite a physical meaning, so we're going to explain that. Okay, probably next lecture. But del cross F, which is also called curl F, give you these results at here. And according to the theorem, it basically says this one needs to be 0 so that the F is considered as a conservative field. Okay. Now, if F is 0, right? If del cross F equal to 0, so then each component of this vector should be 0. So then you get 3 different equations. Okay. So if the 3 equations are satisfied, then you get a 0, right? All zeros, then you get this vector field is conservative field. Not good? Yeah. All right, so I'm not going to prove it here. So there's a very simple proof to show in the lecture notes, but this is basically how you can show whether a vector field is conservative or not. All right. So let me show you an example at here, how to use this theorem. Okay, let's consider the following vector field. Okay, so here's a vector field. And without applying any theorem, we don't know what kind of vector field is, but we want to show whether this is conservative field or not. So this is a 2D field, right? So which is great. This is just M, and this is just N. The component P, right, technically 0. Then I'm going to use this cross product here to verify if this vector field is conservative or not. So calculate del cross F. Then apply the formula IJK. And here, the second row is partial X, partial Y, partial Z. Third row here first is M. So that's M over here. So you could just write M here. And then N last is 0, right? So P is 0. Okay. And because this element is 0, so you actually end up with a very simple result. Basically, you end up with just the key component. So if the P is 0, you don't have the I component, the J component, you only have the K component. Okay. They're only a vector pointing to the Z-axis direction. So now let's calculate what is partial N partial X. Right, so this is a partial N partial X. Calculate based on the N function. Partial derivative with respect to X. You treat the Y as a constant. So you get 12xy from the first term. The second term, you get 6y, you got what? 3y squared, right? Consider y as a constant. Then partial M, partial y, consider x as a constant. Okay, then you get 12xy and minus 3y squared. It's clearly that these two are the same, so that means the del cross F, right, equal to 0. So everything is 0. If F is 0, that means this vector field, right, is conservative. Okay, that's it. So it's a very simple application of this theorem. You just have to calculate the cross product. If it's 2D vector, then you save yourself a lot of computations. You only looking at these two, comparing these two partial derivatives. Okay, and then you can make a decision whether you have a conservative field or not. Okay, all right. So we still have a few minutes here. So then remember the second question, right? Second question: if f is a conservative, then how do I find a potential function small f so that its gradient give me back this conservative field? Okay, so let me show you how to do that. So what is the potential function? f. And because this is a 2D, so we're looking at is a scalar function of two variables, f of x, y. Okay, so here's how we can find the f. It's involving multiple steps at here. So what do we know, right? So what we know is this is a relationship between the conservative field f and the potential function small f. Okay, so that basically means partial f over partial x equal to m, and partial f over partial y equal to n. And this is the connection. And this is the clue. Those are the clues that we're going to work with to find the small f at here. So you end up with two different conditions. Okay, so we have to make use of both of these. But let's start from the first one. Partial f partial x equal to m. What's m? M, we already have it. M is 6xy squared minus y cubed. Okay, so this is your m. Okay. So when you calculate partial f over partial y, you get this result. And when you calculate the partial derivative with respect to x, what do you treat the y as? Constant, right? So if I give you a question like this, let's see, df over dx equal to 6x minus a constant 2 or 3, whatever, right? Then what can you do to find the small f, the function f? What you do, you multiply the dx over here, then you integrate both sides, then you can get this function f, right? So that's exactly the same thing what we're going to do here. Then I'm trying to obtain the function f of x, y. Then I'm going to integrate basically both sides, but I'm integrating 6xy squared minus y cubed and dx at here. Okay, so I'm integrating this function. I'm only integrating with respect to x because I know at this stage my y is considered as a constant. Now, if I integrate a certain function, single function x, so you get an antiderivative, and technically you should also add what? A constant c. So then over here, right, if I integrate both sides, and I should also add something, right? But I cannot just add a constant c, right? Because technically there's a y here. Or in other words, if I take a partial derivative of f with respect to x, okay, I should get back to this term. So whatever I added it over here shouldn't affect this partial derivative, partial f, partial x. If you add a constant c, of course, it does no effect. But technically, you should not add a constant c. You should add a what? You should add a function of, exactly, function of y, right? If you add a function of y, let's see, does it affect the partial derivative? Because you're going to calculate the partial derivative back to x, then whatever function y you added here will disappear, right? Because it's constant, considered as a constant. So let's use a r in here instead of c, right? Yeah. So that's the results of this step here. To integrate both sides, you need to add a constant, not a constant, but you need to add a function of y because this is a partial f over partial x, okay? So let me finish the example. Let me just, it's a little bit hanging cliff here. All right, so now you calculate this derivative, this integrals at here, okay? You integrate it with respect to x, consider y as a constant. So what do you get? You get 3x squared, y squared minus x, y cubed, and then plus the function of y, okay? right? When you integrate this, always remember you're considering y as a constant, right? If that bothers you, you can temporarily replace the y with some sort of a constant, right? And remember to replace it back with a y. Okay. All right, so this first step here, we end up with an expression for this scalar function, potential function, but there is a little bit of uncertainty here. So then what is this Ry, right? We still couldn't solve this one yet. Then you go back to your second condition. We haven't made use of this condition yet, right? So the result of this is based on this first partial derivative. And we had to make use of the other partial derivative. So the other partial derivative is to calculate partial f over partial y equal to n. Now we got the partially what the f is already. I have my f's right here. So I can actually calculate its partial derivative. So calculate partial derivative based on each one of the term, and you end up with, right? What do you end up with? You calculate the partial derivative of the partial results that you have obtained from the previous step. Okay, and you end up with the 6x squared y minus 3xy squared. Okay, and the last step is partial derivative, but this is not a really partial derivative, it's just a straight derivative, right? Because this is just a function of y. And what does this equal to? This equal to n, and n in this question equal to 6xy squared minus that. Okay. So this is your n here. Okay, this is your n. So what's nice in this question is you actually canceling these two terms on both sides. So you end up with just a dr over dy equal to 0. Okay. When you have a derivative equal to 0, the r literally means what? The r is equal to, what's r? Constant, right? Any constant. Okay. So all you have to do is replace the r with a constant. Now, sometimes we don't really need to use a constant. You can just actually pick a very simple value, maybe 0 in this case is the most simplest answer, right? Technically, you add a constant at here, but you could just use a 0 at here, and that would be considered as a right. Okay, so this is your potential function. If you calculate the gradient of this function, then you get back to your vector field, capital F. Okay. So I can go through this question a little bit more at the beginning of the previous next lecture, right? But take a second look at this example. I rushed a little bit, okay, at this stage, so apologize for this late dismiss. Okay, any questions? All good? Okay, feel free to come over if you have questions.